Okay. Now, I would like to introduce to you a very interesting application called the Trans Multiplexer. So, the Trans Multiplexer application. First, let me give you a structure, a figure for you to analyze and do it very quickly, and then we will. So, I have 3 signals. Let me call them as x naught e of j omega. The spectrum of this signal between 0 pi and 2 pi is as follows. Straight line here. Okay, so it is a complex signal. X1, choose a different color, x1 e of j omega, magnitude 0 pi 2 pi, the spectrum, it is a real signal, but it is a sort of a, it does not have low frequencies, it has got high frequency content. Okay. Third signal, x2 e of j omega, magnitude, and again this has got a very different type of behavior. It is flat, a small dip around pi, and then goes back up. Okay. These are just randomly chosen spectra, nothing special about the spectra themselves. Okay, just some of them are complex, some of them are real low pass. This one looks like a signal that has got all frequency components. So the important thing is what we are going to do with the processing that we are going to do with these 3 signals. I am going to feed x naught of n to a multirate structure, which is first going to upsample by a factor of 3 or insert zeros, followed by f naught of z, where f naught of z, let me just draw the filter here. This is pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, 2 pi. Okay. So, the first of the filters f naught of z goes from minus pi by 3 to pi by 3. So, the image would be located here. Okay. The second filter is h of that one goes from pi by 3 to pi, and then the third one goes from pi to 5 pi by 3. Okay. So, this is f naught, magnitude f naught, this is magnitude f1, this is magnitude f2. Okay. And the structure that we have is this output gets added along with, take x1 of n, upsample by a factor of 3, pass it through a filter f1 of z, and then add it to this point, and the third, and the arrows are going in this direction. Okay. The third one is the green, it is x2 of n upsampled by a factor of 3, pass through a filter f2 of z, which is then added on to the original signal. Okay. So, here is the signal flow. Please tell me what the output signal, let me call this as S of n. S of n is a combination of these 3 signals. I would like to understand what the spectrum of S of n looks like. Okay. And so, the first thing you would do is each of these gets upsampled by a factor of 3. Let us do it for x naught, and I will assume that this you will be able to do it for the others. So, the first step would be x naught. basically this is pi by 3 pi and 2 pi. Let me just draw it equispaced, it will be easier for me to sketch it. So, pi by 3, 2 pi by 3 pi, 4 pi by 3, 5 pi by 3 and 2 pi. Okay. So, now if I upsample by a factor of 3, I am going to get 3 repetitions of the image. That is first repetition, second repetition, third repetition. Okay. And I am going to pick off the, so before that is this one. So, the first branch is going to pick off the portion from minus pi by 3 to pi by 3. Likewise, if you look at the other 2 branches as well, then what we get is, in the second case you will get this portion of the spectrum, second branch. The third branch, the portion of the spectrum that gets retained is from here, and so if I add the 3 together, the combination of these 3, then the signal that we get is a signal that looks like this, from minus pi by 3 to pi by 3. Then the red portion, okay, I am sure you have already probably finished before me. This is the red portion going all the way to pi, and then the green portion, and then finally you will get one more, the other part. Okay. So, this is what the spectrum looks like. Okay. So, this is what the spectrum looks like. Okay, I hope you basically got the structure. This is 0 and this is 2 pi. Okay, and just to show the frequencies below minus 2 pi, I have just shown below 0 just for a short portion, so that you know how the signal pattern repeats itself. Okay, so what the structure actually did was to do something like equivalent of modulation. What it did, because it took these are all baseband signals, it took one of them, it retained, it kept it as a baseband signal, the other 2 it actually moved it up in terms of the center frequency. So, what you find here is a translation of the basic spectra, and so in some sense multirate signal processing can be used for modulation, because it is very easy for us to shift the center frequency of any signal spectrum. So, this is one principle of that. The other element of what this structure is doing is that it took 3 signals, right, it took x0, x1, x2. So, you can think of these as 3 signals in the time domain. You can think of them as time division multiplex signals. So, basically you could have a part where there is a green sample, there is a red sample, and then there is a green sample, then again the blue repeats, red and the green. So, basically you can think of them as interleaved, you de-interleave them, pass it through each of those branches, and then what you get here at this point, so from time division multiplexing you go to frequency division multiplexing. You get a single signal where the spectra of the signals are suitably shifted. So, that is called a frequency division multiplex signal. So, this is why the name transmultiplexer is given, because you went from time division multiplexing or time domain multiplexing to frequency domain multiplexing, frequency division multiplexing, and this is a very useful structure in multirate signal processing. It also turns out that it is very useful in communications as well. We will establish the link in a minute. So, anytime you do the transformation from time division multiplexing to frequency division multiplexing, we must be able to do the reverse operation. The reverse operation basically says take each of these signals, or take this signal S of n, pass it through a filter. It could be F naught itself, just for I will just call it as H naught of Z, where H naught of Z shares the same spectrum as F naught, and H1 shares the same spectrum as F1, and H2 shares the same spectrum as F2. So, basically the structure is going to be H naught of Z, which is a low pass filter, followed by a downsampling by a factor of 3. Okay. Please confirm or verify that you will get back the original X naught of n, assume the filters are perfect. So, the same input signal, I pass it through a band pass filter H1 of Z. It has a total bandwidth of 2 pi by 3. So, I can downsample without aliasing, downsample by a factor of 3 and then get back the original signal. Hopefully, this is X1 of n with a tilde, that means it should be as close to the original signal as possible. This is X naught tilde of n, and the third branch, same input signal, pass it through a band pass filter H2 of Z. This can also be downsampled by a factor of 3, and this should give me X2 tilde of n, and these are hopefully very close to the original signals themselves. Notice that you have once again you have brought everything back to baseband, because these are not at some higher center frequency, they are all centered around 0. So this operation basically does the in reverse conversion. It does the frequency division multiplexing back to time division multiplexing. You basically have separated out the signals in so that they can be treated separately or independently in the time domain. Okay. So, what have we done? What is the what have we discussed so far? We have taken a set of parallel signals, upsampled them, passed them through uniform filter bank, right, appropriately shifted filters. We showed that this process or this computational step translates each of those frequencies into non-overlapping signals with suitably shifted center frequencies. At the other end, if you want to separate them out and bring them back to baseband, you have the reverse operation. The filters look identical, basically they have the same responses, and then the downsampling brings them all of them back to baseband. Okay, now here comes a very important element in our discussion. Why did we do this discussion so far? Now, if you have already, I am sure all of you would have studied OFDM in digital communications, right? Everyone would have studied. You can open any transmitter, OFDM transmitter. So this is what you will find. You will get basically you will let me write it as some QAM symbols. Okay, let's call them as S0, S1 ... These are QAM symbols. Then the first step of this process will be a serial to parallel converter, where you will split this into parallel streams. Let's say that there are m parallel streams. So this is number 1, number 2, this is number m. And what we do next in the OFDM transmitters is that you take a m point IDFT. This is a IDFT of size m. Okay. Now these signals, so let me just label them. I think maybe the convention that you would have used, let me just use the same convention. You probably would have labeled these signals as uppercase x of 0, this one as uppercase x of 1, this as uppercase of m minus 1. Okay. Okay. Even if you did use something slightly different, we will assume that this is the labeling scheme that you have followed. This will produce for you, after doing the IDFT, it will produce for you a set of M samples. Those are typically referred to in terms of lowercase x of 0, x of 1, x of m minus 1. Okay. And after this, you would have had a parallel to serial converter. So, what would be the output coming out of this block would be the lowercase x naught of 0, x naught of 1, x naught of m minus 1. So, one block of data you converted from input stream, you parallelized it, took the IDFT and then did a parallel to serial conversion. Okay. Everyone agreed that this is the standard transmitter of an OFDM block. Okay. Now, here is where the interesting part comes. Can you please tell me how you would, having studied the multirate part, how you would characterize this portion? Parallel to serial converter, we have already seen, is nothing but a parallel, you upsample by a factor of m. Each of these streams you upsample by a factor of m and then add them with suitable delays. Am I right? So, the next stream will be upsampled by m, it will pass through 2 delays, and so it gets moved 2 units to the right. So, dot dot dot, the last one is upsampling by m, passing through m minus 1 delays and eventually getting to the output. Okay, so, this portion is this. So, this parallel to serial converter in our structure is nothing but a bank of upsamplers followed by delays, and then you add them to the other side. Okay. Now, IDFT followed by a filter bank, IDFT followed by a filter bank. Okay. So, basically if you go back and look at the structure that we derived, followed a delay chain followed by the IDFT, basically tells us that the filters are shifted versions of it. So, in other words, if you now combine this multirate structure that we have with the IDFT, this basically says that the first branch basically is a filter bank that has this type of a response, that is the first branch. The second filter is going to be shifted, is a shifted version. Okay. The third one is a basically it's one more shift. Okay. So, you can see that these are the shift, and if you now want to think about it as moving the interpolator to the front, okay, what is it doing? It is a transmultiplexer, because a transmultiplexer structure, what does it have? It has got basically the one that combines them has got the upsamplers followed by a filter bank. So, what is the OFDM transmitter? What the OFDM transmitter format? Basically is nothing but taking these symbols x naught, x1, x of m minus 1 and applying it to these carriers, and then doing a frequency division multiplex signal. That is OFDM. Okay. So, in other words, the tools that we have developed, the insight that we have developed in our multirate framework, where we say that okay, if I have the IDFT, it is actually not just a transformation, it is actually a filter bank. The underlying filters are a DFT filter bank, they basically span from 0 to 2 pi. So, once you have that understanding, and you can say that okay, parallel to serial conversion is nothing but a delay upsampling block followed by a delay chain. The IDFT combined with it is a bank of filters, and then actually what we have done is so in other words, what have you done in OFDM? So, in OFDM, the basic principle is as follows: whatever is your bandwidth 0 to 2 pi, you think of it as divided into number of narrow carriers, okay, and the number of carriers, this is, so basically each of these lines is a center frequency. So, this would be carrier number 0, carrier number 1, 2 all the way to m minus 1, because this would again limit to, this is 2 pi, okay. So, that would be the carrier frequency. So, now if you were to think of it in terms of the bandwidths, you would have to draw it in this fashion. So, the bandwidth is actually, this is channel 0, this is channel 1, and the center frequency channel number 2, and channel m minus 1 is situated here. Okay. So, what is the OFDM transmitter actually doing? The OFDM transmitter says okay, channel number 0, you please transmit for me symbol S0, some QAM symbol, okay, and it says okay, channel 1 you transmit S1, you transmit S2 ... And at the other end, what would you do? This is an FDM signal. What would you do on the other end? You would do the inverse operation. You would basically convert it from a center frequency back to baseband and then pass it out. And what will that structure be? Structure will be the reverse operation that we have done, where you have filters followed by downsampling. Downsampling is a demultiplexing operation, which is very straightforward. We know that that is a series of delays followed by a downsampling chain. Now, when you to cancel out the IDFT, you will have the DFT sitting there, and once you cascade this together, you find that you now have a very different interpretation of OFDM. It is not just the IDFT or IDF. So, it actually is leveraging the fact that you have a filter bank sitting there. The operation is that you have taken your spectrum, divided it into narrow channels, and you are transmitting symbols on each of those carriers. Okay. Now, the advantages of OFDM become very powerful if one particular channel is not good. Let us say this channel was not good, it had, for some reason it had either interference or lot of power. You can choose not to transmit anything on that. So, in other words, you can transmit S2 on the next carrier. So, that is point number 1. You can choose to omit certain carriers which are undesirable. Okay, that is a huge advantage. And where does the insight come from? When you treat it as IDFT, you say, I don't know, maybe one channel got 0 sample. No, that is not the way to interpret it. You interpret it as one of these channels has got a lot of interference, or the signal to noise ratio is not good. So, you have chosen not to transmit anything on that particular carrier. Okay. The other element is that you can transmit all of these signals with the same power level, that is normal DFT. Okay. Or if you can look at your constellation S0, S1, you apply them, all these symbols are coming at the same power level. Now, if you found out that, for example, S1 had got very good signal to noise ratio, okay, then how would you take advantage of it to maximize capacity? So, what you would do is you would boost the power of this particular signal, right. You would transmit more power on S1. So, in other words, the spectrum would now look like you had, this is S0, and then S1 alone you are transmitting with a lot of power, and then all of the others at normal power, let us say. Okay. Now, how do you achieve this? You could scale S1, apply more power to S1 and then pass it through a normal DFT, but that would basically mean that you are transmitting more power on this channel. Now why would you transmit more power if the signal, the channel is already good? In that case, if this was a 4 QAM, you may be transmitting a 64 QAM on this particular carrier. Okay, that is how you achieve capacity. This is related to the concept called water filling. Okay, water filling basically means that when you have certain channels which have got good signal to noise ratio, you allocate more power to them compared to the other channels. And why would you allocate more power? Because I can send more bits per symbol on those channels. So you can see how the OFDM and all of its advantages actually come into play in a very nice way in terms of our understanding of the OFDMs and its use in a wideband system, primarily from the transmultiplexing operation.
So what are these QAM signals you are talking about?
Okay, so basically if you have a sequence of bits that you want to transmit, so the modulation method basically says combine them into sets of, if you want to combine as 3 bits, then you will have 8 values, and you may transmit these, let me take 4 bits, it is easier to do 4 than, so if I take 4 bits, then I will have 16 possible values, and the possible symbols that I will transmit are one of these 16 QAM symbols, quadrature amplitude modulated symbols. So rather than transmitting it as 4 bits, I transmit one symbol, let us say 011, let us say it was this particular one, this amplitude and phase. The information is carried in the amplitude and phase. So I transmit one symbol with a particular amplitude and phase, which the receiver will then detect and then will map it back to 0111. So I do not transmit 4 bits, I transmit one symbol which represents multiple symbols. So each of these are actually these QM symbols. You have taken the bits and you have grouped them into the appropriate constellation, and then you are transmitting this information not on a single carrier. This is why it is called a multi-carrier transmission. The OFDM is called a multi-carrier transmission, because what you have is actually a bank of carriers, and each carrier you have placed one symbol appropriately, and then you combine them. How did you combine them? The transmultiplexing operation. Basically you shifted them in frequency and combined them, but that comes for free when you use the IDFT with this particular structure. IDFT and this structure actually implements a filter bank for you. So when you apply them, you automatically get the translation from time division multiplexing to frequency division multiplexing, and therefore and of course this also gives you a lot more insight into when do you not transmit on a particular channel or on a particular carrier, when do you boost the power of a particular carrier. Again, all of these are flexibilities that come into play when you have an OFDM system. Now the other element that which we have not touched upon today is when you do an OFDM transmission, there is one more element that is in this one. What is that? You insert something called a cyclic prefix. You take this data output, you take some portion of it and then move it back and call it the cyclic prefix. Okay, something called a cyclic prefix, CP. Now CP also has got a beautiful explanation on the context of multirate signal processing. Okay. So when we actually get into this is not the entry point into OFDM, this was more of, okay, we have finished filter banks, we are going to actually look at the maximally decimated filter banks for some time. So it is not the application area. OFDM is one of the applications. I just wanted to already establish for you the link to OFDM. Now once we have this in place, we will come back and analyze it. The next chapter that we will be studying is actually OFDM. We will once again revisit this issue and understand, how OFDM works, why is the multi-rate signal processing, where are the insights that we get, why cyclic prefix, how long should the cyclic prefix be. All of those questions get answered once you have a DSP perspective on what is happening in the channel. Okay, so what is the actual topic that we are going to do next is an M channel maximally decimated filter bank. So basically you have the analysis filters each channel is, each of them is has bandwidth 2 pi over m, and each of them can be downsampled by a factor of m and then reconstructed. So basically this is the broad framework that we would analyze, and we will spend our time analyzing m equal to 2. That gives us a lot of insight, and basically we will leave the general case as a basically a theoretical framework, not spend too much time on that, but good insights that we will get from here. We will pick it up from here in tomorrow's class. Thank you.